Hello folks! In the previous video, we explored together the theory behind service redirection in VXLAN L2VPN eVPN fabrics, leveraging group policy option or GPO. Now, it's time for us to take what we've learned and put it into action. In other terms, in this video, we are going to make things practical and hands-on. What I mean by this is that we are going to consider a typical real-life scenario where we want to take the traffic from a client to a server and see together how to redirect it through a firewall. Well, actually, the traffic that we are going to redirect is not the one that we would typically redirect in real life. You are going to see this soon enough. But the global ID is typically what we would need to do. So we will take the time to cover all the configuration process step by step and try to really understand what is behind each and every line of configuration. Then we will push everything into a lab environment, and once we've done with the configuration, we will check together that everything is working smoothly, properly, as expected, etc., with some useful, handy show commands. So let's get started. Before we dive into our lab environment, I would like to take the opportunity of this video to make some very quick updates in regards to what we covered in the previous one. So if you remember, in the previous video, we checked together plenty of constructs and very important terminology elements, among which we had what we call a service chain. So a service chain, if you remember, it is nothing but an ordered sequence or list of what we call services. For example, let's say that at sequence 10, we have a service firewalling. At sequence 20, we have a service IDS. At sequence 30, we have a service TCP optimizer. And the generic ID is to say that we are taking the traffic from an ESG, for example, clients, to an ESG server. So ESG being endpoint security groups. We want to allow this traffic, but before we allow it, we first want to redirect it through a service chain. It means that the traffic will go respectively in order through all the services of our chain. So we will first be redirected to the sequence 10, then the sequence 20, then the sequence 30. And inside each of our services, we can have one or multiple service endpoints. For example, let's say we have two firewalls, firewall 1 and firewall 2. These are service endpoints for our first service. Then let's say, for example, the IDS, we have 3 of them. We have IDS 1, IDS 2, IDS 3, etc. So you got it. And the solution of enhanced PBR leveraging SGACL, what it does is that not only it will redirect through each service, but it will also ensure that multiple traffic flows are load balanced between the different service endpoints that we have inside each service. It means that, for example, for the traffic from A to B, we will pick firewall 1 and IDS 2. Then let's say here we have just one service endpoint, TCP1. Traffic from B to C would take firewall 1, IDS 1, TCP 1, etc. Obviously, for the return traffic between our source and destination, we would use exactly the same service endpoints that we crossed for the forward traffic, so that we ensure symmetry and we ensure to not drop any of our traffic. So this is what we mentioned into the previous video. If you'd like to have more details on the theory, I would invite you to check that video. It's the third one of our playlist. But what I wanted to mention here is that in the previous recording, I was highlighting a limitation that was present inside the first release that introduced the support of ePBR with SGACL. It was the fact that when we configure service chaining, we could only have just one sequence inside our chain. Now, in the latest release, which is as of today, the 10.5.2, this limitation has been relaxed. It means that now we can include up to 5 service functions in a chain. So if I want to leverage the example I have on my screen with 3 service functions, this is now perfectly possible. So I just wanted to highlight this. This limitation is no longer present with the latest enhancements. And speaking about enhancements, actually there are other ones that are interesting. This one, sorry, I've lost my pen again. It says that the sources and the destinations of the contracts can be in the same site, but can also be into multiple sites. It means that we have the support for single site and the Cisco implementation of multi-site, meaning the deployments and designs that leverage border gateways. And finally, when it comes to the distribution of our endpoints and service functions inside VRF, here we have also big flexibility because we see that the sources and the destinations can be in same VRFs, but can also be in different VRF contexts. And for the service endpoints, that can also belong to source VRF, destination VRF, or any other VRF. So the key takeaway is really to check at each point in time the release notes of the latest releases, because enhancements keep being added. So it makes sense, right? When a new feature is published, usually the support is quite limited for the hardware that supports this feature, for the capabilities that we can enforce with this feature, etc. But as time goes on, new enhancements are being added and flexibility come with those enhancements. And also very quick notes regarding the fail actions, because this is a command that will pop inside our configuration. We also checked it into the previous video, but just to clear our minds, I want to mention that when we create a service chain, in every service sequence, we can define what is called a fail action method. What does that mean? It means that this allows us to state what do we want to do with our traffic if we have lost one service of our chain, sorry. So for example, let's say that both firewall 1 and firewall 2 are lost. Both of them, it's important, okay? We have a Murphy's law and we have lost both of them. It means that we have lost actually the sequence 10, which is service firewall. What do we do with our traffic? The default action is to drop the traffic. So if we do not configure any fail action for the sequence 10, and we have lost our service of the sequence 10, we will simply drop the traffic. We can have another action that we can configure. We could configure the bypass option, bypass fail action. What would that mean? It means that if we have lost our service, we would simply go ahead and evaluate the next sequences of our service chaining. So we would simply go and check the sequence 20 IDS, sequence 30 TCP optimizer, and then forward the traffic to the destination. The latest possibility is the forward, which is mentioned here. But we need to keep in mind that forward action, we can configure it only if we have a single service in our chain. And what it would do, if we lose that service, we would simply just exit completely the service chain and forward the traffic based on the routing table. So this what would be done. But typically we would use either drop or bypass from my understanding and my experience. So that's it for the things that I wanted to update. Now we can check our lab environment. Okay, so on the screen here, you can see what will be our playground. Let's explore it into more details. So as you can tell, here we have a classic fabric, VXLAN L2VPN, eVPN. At the moment, in the configuration, there is really nothing fancy, meaning we have configured the underlay, the BGP L2VPN, eVPN peerings, and one VRF and some networks that I will present into the next slide, but that's really pretty much it. We have nothing else configured when it comes to the ESGs or the contracts, etc. This we will configure together, okay? So we have 4 leaves. They are all standalone. We have leaf 1, leaf 2, leaf 3, and leaf 4. Thanks, Captain Obvious. More seriously, on the leaf 1, we have what we will call host 1. On the leaf 4, we will have what we will call server 1. On leaf 2 and leaf 3, I have on each of these leaves one firewall. So on leaf 2, I have firewall 1, and on leaf 3, I have firewall 2. The thing I do want to highlight in this slide is that both my firewalls are 2 arms, okay? It means that they have one arm that we will call firewall in leg and one arm that we will call firewall out leg, okay? A quick step back. In the examples that we will configure together, etc., we will follow, what I presented on the screen, meaning the firewalls with the dual arms. I really want to mention that the logic for firewalls with just one arm is really exactly the same. There are just two lines in the configuration that we would need to adapt to reflect the fact that the firewalls are one arm, but really that's just it. For the logic behind, for how the labels are swapped, really all the process for the redirection, it doesn't make any change if we have two arms of one arm. And to be transparent, in the beginning, I did all my slides and all the preparations with just one arm firewalls. And in the end, I realized that it would be easier to present stuff with two arms, because with the two arms, we can really visualize the ingress and the egress sides of the flow. And I think for when we are starting to learn and for the learning gap, it's easier when we can really separate the two, logically speaking, for our brain. But this is the only reason why I decided to go for two arms versus one arm. It's because it's easier to explain and easier to understand and, to have the global logical representation in our minds. So that's it. Okay, let me come back to my slides and again move to the upper part. And in all the next slides, the firewall in leg, I have tried to be consistent with the color. It will be in purple, and the firewall out, it will be in orange. So all the other colors, they do not make any sense. It's just a way to highlight the stuff, but I tried to have always the in part in purple and the out part in orange, just to ease, finding the correspondence and what every line of configuration refers to which leg, just to ease the follow-up. Okay, so that's it for the lab environment. Now let's check what we will have from a logical perspective and configuration and goals for our lab. Here we have just one VRF. Inside this VRF, we are attaching everything, the host, the server, and the firewalls. The VRF name is the blue VRF. Then we have a couple of SVIs, as you can see. Let's check them together. But first things first, I want to mention also that we are using a kind of addressing convention, quote unquote. So the third digit here is representing what is our SVI. For example, SVI 10, here we have the .10, SVI 20, we have the .20. And when it comes to the Anycast gateway, it is always the 254, okay? So first we have the SVI 10. In this subnet, we have just one host, so our host 1 that is attached, and its IP address is 192.168.10.1. Then we have the SVI 20. In this subnet, we are deploying our server 1, which is there. It has an IP address in 20.1. Then we have our SVIs for the in leg and the out leg. So both the in legs, we will be putting them into the SVI 110. So into the subnet 110, sorry. So firewall 1 has the in leg in 110.1, firewall 2, the in leg in 110.2. And the last SVI, sorry, the 120, it helps us to connect the out legs of our firewalls. So the first firewall has an IP address for the out leg in 120.1, and the second firewall, it is 120.2 for its outside leg. And also, another highlight, it's that we could have the inside legs of our firewalls distributed into multiple subnets and multiple VLANs, meaning attaching to the fabric through multiple SVIs. We could have this. It doesn't matter. It's not an issue at all. It's just from a simplification perspective that I put both of them for the both of the firewalls, meaning both my two in legs ends up into the SVI 110, and both my out legs ends in the SVI 120. But I could have had, for example, 110 here, 130 here, 120 here, and 140 here. It doesn't matter. What is important is that still, if I have two arms, the ins and the outs, let's say it like this, are different. This is what matters. But apart from this, we could have different SVIs if we want to for our different firewalls. Okay. Now, let's check what will be the goal of our lab environment. First, we want to create a security group that we will be naming clients, and we will attach to it the tag 100. You see me coming. In that security group, clients, we will be adding the host one. So this one will be put inside the ESG clients. Then we will create the security group servers. We will assign to it the tag 200, and inside the security group servers, we will add our server one. So this one will belong, this one will belong to the ESG servers. And then we will be redirecting and permitting some traffic from the client to the server. So we will have two use cases. We will have a use case where we want to simply permit the traffic from the client to the server. So this use case is to permit the ICMP and to permit the telnet. And this is what I was mentioning into the introduction, is that typically telnet, we deny it completely from our environments, right? Actually, it's not even a feature that is enabled by default. So again, this is not the type of traffic that we would allow, not at all, not even through redirection. And here I am allowing it even with no redirection, but it's just a global ID, you know, because it's easy to test telnet and see where it goes, etc. But that's it. So long story short, we will be permitting the ICMP back and forth and telnet from host 1 to server 1 directly. So it means if we launch a telnet from host 1, we will simply be allowed directly to the server 1. On the opposite, for the SSH, we are going to redirect it through the firewalls. So the SSH will go to one of the firewalls through, obviously, the inside leg, come back, and then go to the end server. Obviously, also, the return traffic would do the same. So come back through the outside leg of this specific firewall and come back to host 1. What I meant by this specific firewall is, again, the return traffic always cross the same firewall than the forward traffic. So here I have just picked firewall 1. I could have picked firewall 2, but you understood it. We are redirecting through the service firewall. And the last thing I want to cover into this slide is this small rectangle that I will be copy pasting through inside multiple slides so that we remind ourselves of the naming convention that we want to follow, because typically this is the thing that we never remember. You know, we state, okay, our service name, we want to name it firewalling, and when the time comes to do the configuration, we think, okay, what was the name of the service, and we type firewall, and that's it, and it doesn't work because the names are different between the different places. Okay, long story short, this is the names that we will be following. For our service name, we will call it firewalling. The service endpoints, we have firewall and 2, so actually those are their IP addresses. As we are going to see in the configuration, the service endpoints, they are represented by their IP addresses. When it comes to the, sorry, let me drink a bit of water. What I was saying. Okay, yeah, when it comes to the layer 4, layer 7 ESGs, we will be using this naming convention. For the in-legs, we will name it firewall in-leg ESG, and we will assign to it the tag 1100. And for our out-legs, we will be using the firewall out-leg ESG, and we will assign to it the tag 1200. What it means, and we will cover this absolutely extensively inside our demonstration, is that the traffic that comes from our inside legs, it will be classified into this ESG, so the in-leg ESG, and be assigned the tag 1100. Again, if you remember, the layer 4, layer 7 ESG is a very specific kind of endpoint security group that was created and invented for the purpose of traffic redirection. And here we are classifying into the data plane, not in the control plane. And when it comes to the firewall out leg ESG, it is the traffic that comes from the purple legs of both the firewalls. This one will be classified into the orange ESG and will be assigned the tag 1200. Now, when it comes to the class map and policy map that we will use to create our contracts and traffic filtering, we will be using two class maps. The first one is the class SSH, which filters on the destination port TCP22. And the second one will be named class ICMP-telnet, and it will have one entry with matching the ICMP and one entry to match the TCP destination port 23. The policy map will be named client to server policy. What it will do is for the class ICMP telnet do a simple permit, and for the class SSH redirect to our service chaining, and this service chaining will be named simply chaining. So I believe that's it for the presentation of this slide. Before we continue, I must be honest with you, I lied a bit for the lab environment. Actually, I do have a physical fabric with the 5 devices that I presented previously, meaning the spine and the 4 leaves. But when it comes to the attached endpoints, I do not have one server, one client, and 2 firewalls. I don't have all this fancy stuff inside my lab environment at the moment. I just have one additional Nexus 9K that I am using to simulate all my endpoints. So this Nexus 9K, I have represented it here, and its host name is simply hosts. I just wanted to highlight this so that when we go inside the lab environment, you are not surprised to seeing just one end device simulating everything. And really from the perspective of the configuration and all the checks that we want to do together, it doesn't make any difference, right? To have real host or simulated host, it's really the same thing. But again, just so that you are not surprised to see just one host. And when I will be, sending some pings, some SSH, etc., you will see some specific interfaces and VRFs that are used as the source and the destination of the traffic. So this is also why I would like to explain the way it is done inside the lab environment. But it's really nothing fancy. I believe we all used this trick inside our lab devices. So, just for the sake of clarity, let me show you quickly what's being done. So what I actually have is 4 physical point-to-point interfaces and connectivities, meaning that this Nexus 9K is connected through one point-to-point interface to each of my 4 leaves. Okay, so this is what is represented there. I have 1.1, 155, 153, and 151 here. Then on each of these physical interfaces, I am using one or multiple sub-interfaces, depending on the number of endpoints that I want to simulate being attached to a particular host, to a particular leaf, sorry. What I mean by this is that, for example, for my host 1 here, I am simulating just one host. I mean, on my leaf 1, I have just host 1 that is being attached. So I'm using here just one sub-interface. Now, obviously, the numbering for the sub-interface, it needs to match the VLAN for the SVI that is attaching the host to the fabric, right? So here I have my SVI 10. It means that my sub-interface here would be a .10. Makes sense, right? Now, when it comes to what is being attached to leaf 2, I have the 2 legs for my firewall 1, if you remember from the previous slide, the purple leg and the orange leg. So the purple leg, it was terminating into the SVI 110, and the orange leg, it was terminating into the SVI 120. So on my 1/55, I have 2 sub-interfaces, the .110 and the .120. And etc. Exactly the same for my firewall 2 and my server 1 here. Here I have the .20, because here I have SVI 20, etc. And when it comes to the configuration of the VRFs, I used multiple VRFs on the Nexus 9K because obviously I need to ensure that the traffic from one specific sub-interface to another one goes out of the Nexus 9K through the fabric to be then forwarded to the remote interface, right? If I don't use VRFs, obviously the traffic from 2 sub-interfaces of the same device, it will remain internal, right? So I'm using sub-interfaces just to force the traffic to be kicked out of the host. So on the 110 here, I'm using a VRF named leaf1 VLAN 10, if I remember correctly, but we will check it again together. again, we never remember this naming, right? This is why it's important to have a rectangle to remind ourselves of what's the naming. Yes, so the latest thing that I want to mention regarding the tricks to simulate everything is that the host one belongs to its own VRF, the server one belongs to its own VRF. Obviously, this has nothing to do with the blue VRF, right? Again, as I was mentioning, this is just to force the traffic. Sorry, the blue VRF, I've written it here. It's just to force the traffic to go outside of the Nexus 9K. And here, actually, these two subinterfaces belong to their own VRF. I don't have two different VRFs here. Why? Well, simply because when I come here, I want to be able to go back there. So what I did is here create these two subinterfaces inside their own VRF and create two static routes for this VRF to say, okay, if you want to reach 192.168.10.1, the next hop is the pervasive gateway of the SVI 110. And if you want to reach the 192.168.20, 0/24 actually, 10/24 and 0/24, 10/24 go to SVI 110, 20/24 go to the SVI 120. Again, really nothing fancy, but just for the sake of clarity, I wanted to mention it. Let me show you quickly what it looks like from a lab environment perspective. Okay, so here I have opened my secure CRT, as you can tell, and we are simply doing a show IP interface brief VRF all on the device that is named host. Now, as you can see, I have the interface 1/1.10 that is into the leaf1 VLAN 10. This is simulating host 1. This subinterface in .20, it is simulating my server 1. And then I have these two VRFs, leaf2 firewall and leaf3 firewall, that is simulating the first firewall, the two legs, 110.1, 120.1. And for the second one, the two legs of the firewall 2, 110.2 and 120.2. Now, if we go ahead and check the learning on the fabric, obviously, we will have all these, sorry, wrong copy paste, all these endpoints that are learned. So let me do show IP route, HMM, VRF, blue VRF. So on the leaf one, I am learning my host one. I'm just checking what is locally learned. So I have the 110, 120. On leaf 3, I have 110.2, 120.2, and on leaf 4, I have the 20.1. So everything is learned properly. This is our first state. And now, obviously, any traffic from any of these subinterfaces to another one is permitted, because I have absolutely nothing configured on the fabric except from the VRF and the SVI, really classic configuration. So for example, let me ping this server 1 from my host 1. So this works. Let me also do a traffic that should not be permitted in the end. In the end, if you remember, what I want to allow is the SSH from host 1 to server 1 through the firewall, but the SSH from server 1 to host 1 should be denied. So let's now check that the SSH in both directions is working, and in the end we should have just one direction working, right? So let me simulate an SSH from host 1 to server 1. So it will be SSH to this one from host 1. Okay, sorry, again, wrong copy paste. So SSH from this one. So it's working. And now let's do the opposite. So SSH to host 1 this time from server 1. So it's working in both directions. Again, the second one, it should be denied once we have done all our configuration. So that's it for the lab environment. Now let's come back to our slides and check what we need to do from a configuration perspective. I hope you recognize this slide. It is actually one of the slides that we covered extensively inside the previous video, which was on the theory. But now I wanted to call it back again, because I would like to make the things that we will configure match to the theory that we have presented. So what we want to configure at the end of the day is summarized here, right? We checked it into the presentation slide for our goals and targets for this video. And let's see how everything matches what's presented as a theory. So first, we want to configure our firewalling service, which is named firewalling. So this is the construct, okay? So this one is being called here. And the firewalling, it is the collection of service endpoints. We mentioned it multiple times. For our service endpoints, we have two. We have firewall 1 and firewall 2. As you can see here, I have mentioned firewall 1's IP forward and reverse address. This is important from the perspective of the configuration because, again, the service endpoints, they are represented inside the configuration by using their IP addresses. And it is crucial that we know the IP address of both the inside leg and the outside leg so that we are able to redirect the traffic. I'm sure you already see why it is important, but in any case, we will be covering it extensively in the packet flow and the construction of the header of the VXLAN, encapsulated packets and so on. But okay, let's do it step by step. And I really want to break the things down, even if it seems obvious, okay? Please bear with me. So, okay, we have our firewalling service that contains the two firewalls. If we wanted, we could configure another sequence into our service chaining. From the perspective of the logic configuration, is just an additional iteration of what we are going to see together. So I decided to have just one sequence inside our chaining. But again, if we want to add an additional sequence, everything that we are going to cover together will apply the same. It's just, again, another iteration. But in any case, we are going to cover all the theory that is needed to add 2, 3, 4 entries inside the chaining. Okay, and speaking about chaining, we said we want to call our chaining simply chaining. I was not inspired a lot. So this construct is mentioned here. And our sequence there, it will be sequence 10. By the way, why sequence 10? It's because I'm used to start with sequence 10 and jump from 10 to 10. You know, it's the best practice that we learn when we start in networking to not do 1, 2, 3, so that in case one day we want to insert a sequence before or after, it's easier. It's just this. Okay, so this was for the configuration of our service endpoint and service chaining. Now let's move to the part of the filtering of the traffic. As we said into the presentation of the goals, we want to treat two kinds of traffics, actually 3 kinds of traffics, using 2 different ways. For the SSH, we want to redirect it to the firewall. So first we need to filter on that specific kind of traffic. So we will create the class map that is class SSH. So it's the one mentioned here. And the match filter for SSH will be a match on TCP destination port 22. So this one is referring to our match filter that is presented here. And then we create an additional class map. Obviously, we could separate the two. We could create a class map ICMP and the class map Telnet. Now, it really depends on the preferences and the flexibility we want to give, etc. It really doesn't matter. I just created one to match the two. So it will be a match any. So either match ICMP or match destination port 23. Okay. So for the ICMP Telnet that is presented here, this is where it fits inside our picture. Okay. Now the step further is the policy map. So the policy map, what it does, it says that if you are matching specific class map, what do we do with the traffic? So we'll have 2 entries. We will say that for our class SSH, we will be redirecting to a service chain. And for our class ICMP Telnet, we will be simply permitting the traffic. Now you might be thinking, okay, what about the deny? We will come back to it a bit later because the way we are going to enforce our VRF will be into enforce deny mode. And if you remember the theory that we covered in the first 2 videos actually of the playlist, we saw that if we do an enforce deny, we are implicitly denying everything that we are not explicitly permitting. But I will come back to this just a bit later, and I believe it will be in the very next slide. Okay, so this was for the for our policy map. Now let's see where our construct for the ESG fits inside the picture. So, oh, okay, I didn't copy the rectangle for the clients and server. It doesn't matter. We said we want to create an ESG client with the tag 100. And the way that we are going to put our host 1 inside the ESG client, we will be matching on the connected 192.168.10.0/24. We could also match on the SVI 10, or we can match on the /32 of the host. In any case, here we are matching on something that is connected to the fabric. And we are putting the host and the server inside their respective groups by the learning inside the control plane. This I have spent, I think, 30 minutes speaking about it inside the previous video, so I will definitely not come back inside the same details, even if I'm really talkative. Okay, so the server 200, the server's ESG, which will have the tag 200, we are going to match on the connected 192.168.20, .0. It's crazy that each time I go through my slides, I see another typo. Okay, apologies for that, but I believe that you got it. So yeah, that's it for the client and the servers. Now for the layer 4, layer 7 ESGs, they are going to fit inside the last column. So the firewall in leg ESG, it has a tag 1100. We are going to match on the interface VLAN 110. And for our firewall out leg ESG, we are going to match on the interface VLAN 120. So here the match, again, you see the difference between the two match selectors, depending on if we are on a classic ESG or if we are on layer 4, layer 7 ESG. Here we are matching on something that is connected and we are inside the control plane. Here we are matching on an interface VLAN 110 and 120. So that's it for our ESGs. And then we have the policy that we will create, which is mentioned here. So the policy map, clients to server policy, it will say that for our source ESG, which is 100, to our destination ESG, which is 200, we want to apply this policy map. And depending on the kind of traffic that we are matching, we will be either redirecting through the firewall or permit it directly. So that's it for the high-level picture of our configuration. Now it's time to cover the details of each and every step. Very quick overview of the way that I decided to split down or break down the configuration, the different steps of the configuration, I would say. First, I put what I called what is similar to quote-unquote basic microsegmentation. What I mean by this is that I'm actually referring to the first two videos of the playlist. Because in those two videos, if you have checked them or if you remember, what we did was simply playing with putting some hosts and servers inside specific ESGs and permitting or denying traffic between those ESGs. There was no notion of service redirection. It was really just enabling the microsegmentation, enabling the feature, enabling the proper prerequisites, and see how we can put the end hosts inside ESGs and how we can permit or deny the traffic between them. So I have two slides on this that refers to what we did inside those videos, and that we are going to need again inside this one to enable the service redirection. Then as a second step, I will be referring to what I call to being similar to classic ePBR, so IP-ACL ePBR, because there are some steps that really are the same that we need to enable if you wanted to configure the classic enhanced PBR, the one that use IP-ACLs, not ESG ACLs. So the second part will be to, say these steps, we would need them also if we do IP-ACL ePBR. And if you did ever configure IP-ACL ePBR, it would make sense, right, to see those steps again for this part. And the last one would be what is really specific to configuring ePBR with SGACL or ePBR with GPO, however we want to call it. This is just a kind of split of the configuration that I decided to make. We could have created other types of, division of the configuration. It's just one way of doing. Anyway, let's come back to the slides. So here we have what is similar to basic microsegmentation. The first thing that we need to do is enable the system routing template security group. This one has also a dependency of doing the reformatting of the SSD and requires a reboot. The reboot is really just to do the reformatting and enable the routing template. Once it is done, we do not need to make reboot if we enable or disable the feature security group. and speaking about that, the next step is to enable the feature security group. So obviously we need to do this on each and every of our leaves inside our fabric. Then the third step is to configure properly the VRF, blue VRF. And here is what we were referring quickly to in the previous slide. We are doing an enforce with a default deny. These are very, very important steps. The enforce, it says that whatever we will be configuring from the perspective of ESGs or contracts, we want to enforce it. The opposite was the unenforced. Unenforced, it means, okay, you can configure whatever you want from the perspective of ESGs and contracts. It will be just sitting there and completely ignored, not even evaluated. When we want to evaluate them and consider them, which is exactly what we want inside our lab environment, here we go ahead and configure enforce. For the default deny, it's what I was mentioning by being what's the kind of traffic that we want to deny between our ESGs. And actually by putting default deny, we are implicitly denying what is not explicitly permitted. Let me rephrase. Let's say that we have different ESGs. So our ESG clients, our ESG servers, let's say ESG client 2. So all these are ESGs. When we are inside enforce deny, implicitly, all this is actually denied. So nothing is permitted. The only communication that is permitted is the intra-ESG communication. Apart from this, everything is denied. So we do not want to think about, okay, I need to create a class map to match this specific kind of traffic to deny it. It is implicitly denied. What we need to do is define the class maps to match the proper filters for the traffic we do want to permit, either directly or through a redirection to a service chain. In any case, what is the traffic that we want to allow? And last, it is the configuration that is needed to put the clients and servers inside their ESG. So very straightforward, we create the security group, we provision the name, we give the tag, and then we match on the connected endpoints inside our VRF for this subnet. So whatever we are learning in 192.168.10 will be mapped to clients. So it will have a tag of 100. Whatever we are learning in 20.0 will be mapped to servers and will have a tag of 200. So far, so good. So let's check the next slide. Here is also something that we did in the first two videos. It was how do we match the specific traffic on which we want to have any kind of action? How do we define this traffic? It is through defining specific type of class maps, which are of the type security. So the first class map we will define is the class SSH. Again, I'm just reminding the names there. Class SSH. It is matching on IPv4 TCP destination port 22. And the second class map that we will be needing is also obviously of type security. It will match any from the entries, and the name is ICMP telnet. So what is the any of the entries is either ICMP or TCP destination port 23 for our telnet. So this is what was similar to basic microsegmentation. Now let's cover the parts that are similar to classic ePBR. By the way, for the explanation of this slide, because from my perspective, this slide and the other one where we define the groups for the L4, L7 ESGs are really the heartbeat of all the solution. So it is very important, in my humble opinion, to be crystal clear on what is behind each and every line of this configuration. Why do we need them? Where they will be used in the background to forward properly the traffic, and also to deduce properly the background configuration that needs to be pushed by the Nexus 9K. Everything, all these points are very important to consider. So I will take the time to cover them. I will be covering a bit of them here. And in a few slides, when we put all the configuration together and we zoom out, I will again give some hints just to clarify the things and have and be comfortable with the whole solution. Because at the moment, as you can see, we are zooming in multiple lines of configuration. So we are not seeing the global picture and the high-level view of the whole configuration. When we see everything, all the configuration that is put together, I will again give some explanations and highlight why we need every line of configuration. But please bear with me on this because it is important. So to be able to enable this part, the classic ePBR, obviously we need the feature ePBR. If we do probing, we need also the feature SLA sender. It's very important to have this feature if we want to leverage especially the fail actions. If you remember in the introduction of the video, we were highlighting again what are the different fail actions. Obviously, if you want to take some action in case of a failure, we still need to detect the failure. How do we detect the failure? By probing and monitoring our services. So for that, we send probes. It can be ICMP, it can be checking a specific port that a specific port is answering. It can be really anything. We can be quite creative, but we need this feature if you want to enable it. For the moment, we are not enabling any kind of monitoring for our services. I will try to record a video on the, I would say, more fancy stuff and advanced stuff that we can do with the redirection. But for now, I'm just mentioning that, okay, if you want to enable fail actions, you need to have the feature SLA sender. Then we configure our service firewalling. So it's this one, right? And in the service firewalling, we are giving what are the IP addresses of the services. So multiple times we mentioned that the services are being referred to by their IP addresses. So where are our firewalls? And if they have two arms, which is the case in our examples, what are the IP addresses of each of their arms? So actually, we are saying that, okay, the IP addresses, we need to look for them inside the VRF, blue VRF. And for information, we are saying the Nexus 9K, and we are telling him, hey, buddy, you know what? The firewalls, the endpoints are, we have two firewalls, actually. We have two services. And these endpoints are 192.168.110.1 and 192.168.110.2. So it is the purple IP addresses. It is the inside legs of our two firewalls. And we are also telling the system, hey, buddy, by the way, we have here two arms firewalls. So please consider that for each entry, we are mentioning a reverse IP, which means here we have two arms. If we had a one-arm firewall, we would still need to put this line, but the IP address mentioned here would be exactly the same than the one mentioned here. It makes sense, right? But still, I wanted to put the two arms just to clarify the separation of the two so that it is easier to understand, comprehend, not sure of the proper term in English. So here are the legs in orange. So these are the outside leg. So the reverse IP of 110.1, it is 121. The reverse IP of 110.2 is 122. And from a high-level perspective, it's really easy to understand why we need this, right? If we need to do some service redirection to someone, we need to define the someone. Why do we need the two IP addresses? It is because, well, if we consider the forward traffic from host 1 to server 1, right, we are sending to the inside leg. So we need to tell this IP address. When it comes back, it is just forwarded to the destination, okay? For the return traffic, we are sending to the outside leg, right? Before it is permitted to the source, to the source of the forward traffic. So for the forward traffic, we need to know this IP address. For the reverse traffic, we need to know this IP address. It makes perfectly sense. So the system cannot guess where the endpoints are located inside the fabric if we don't tell it. Obviously, when the firewalls are connected and they start to sending ARP, through the HMM process of each leaf, we are learning the IP address of 110.1, 121, etc. We are propagating these IP addresses across the fabric, etc. We won't come back again to all these details, but that's basically how it works. So this is why it is very crucial to have this part, this configuration block that is actually saying where our firewalls are connected. Now it's time to check what is really specific to the SGACL ePBR part. So actually we have, I would say, two blocks of configurations that we need to put. The first one, it is this one. it allows us to actually define the layer 4, layer 7 ESG selectors. So here we are defining our endpoint security groups the same way that we define the ESGs for client and servers. The only difference is that those ones are specific L4, L7. So inside both of them, we need to state that we are having type layer 4, layer 7 ESGs. And inside of them, we are matching on the interface. So for the security group that is purple, 1100, that corresponds to the firewall in-legs of basically of our firewalls. So firewall in-leg ESGs. Here we are matching on the interface 110. And for the security group 1200, that corresponds to the firewall out legs of our firewalls. So this ESG, we are matching on the interface 120. What does it mean? It means that any traffic that comes through the purple legs will be classified in the data plane inside the tag 1100. And anything that comes from the orange leg will be classified in the tag 1200. I'm sure that I'm doing quote-unquote oral typos that I will discover in the edition and that I will need to correct using text popping out on the screen. I apologize for the mess up that I can bring. You know, it's very difficult to focus on all the numbers, especially that the numbers come in my head in French. So I need to do live translations in my brains live. It's not always easy, so apologies. I hope you can still, I'm too messy for you to not be able to follow. So at least trust what's on the slide rather more than what I'm saying live, okay? So coming back to the slides. So here we have defined our ESGs. The second part is to add this line, and actually this is a crucial line inside our service firewalling. So the one that we defined inside the previous slide, where we were giving the endpoints. So here we were giving the endpoints, right? And inside here, we were missing actually one line that is mentioned here. So here we are saying that the service firewalling actually is being mapped to two security groups. The first one is 1100 and the reverse one is 1200. Let me step back a bit because actually, at least for me, this was the main learning curve that I needed to cover to try to understand the logic behind the configuration. The key solution to ease the understanding is really to imagine how you would do personally if you had to solve the problem of traffic redirection inside the fabric. Let me rephrase. When you configure a contract, right, and you say, okay, from 100 to 200, I want to cross a service 1 with sequence 10, a service 2 with sequence 20, and go to 200. In your mind, what your brain does automatically is those waves that I keep drawing on all the slides, and it makes the slides actually a bit messy, but you know, immediately you draw this. And what's the way, what do you use, sorry, to draw these lines? Well, actually in your mind, it's clear when you are enabling the sequence 10, when you are enabling the sequence 20, when you are enabling the sequence 30, because it's easy to follow, right? From the perspective of a human being. From the perspective of the fabric, it's not that straightforward because you need to help the fabric understand where it is from the perspective of the chaining. How does it know if it should apply the sequence 10? How does it know if it should now apply the sequence 20, etc.? Because at the end of the day, it's just one traffic circulating through the Nexus 9K. The Nexus 9K will receive the flow, it will check the flow, and it needs to take a decision. But you know, you are not inside the Nexus 9K to tell it, hey, buddy, you know what? Here, you should redirect to the service 2. It's not the first hop. It's actually the third or the fourth hop inside our chain. So how do you do to give this intelligence or this knowledge to the Nexus 9K? Actually, this is why we needed, this is why the engineers needed to introduce something to help with the service redirection. And actually this something is the layer 4, layer 7 ESG, and this specific tagging. Okay, so now let's consider our traffic going from host 1 to server 1, and just for the sake of demonstration, let's assume that it will cross firewall 1. So it is firewall 1 that will be picked for this traffic among the two. So the traffic is received by leaf 1. It will check the destination. It will see that the destination is inside the group 200. It will check the source. It will see that the source is inside the group 100. So what it will do is apply the set next hop. So the set next hop, which was corresponding to this IP address. And it will send the traffic across the fabric. It will reach leaf 2. Leaf 2 will decapsulate the traffic and send it to the inside leg of the firewall. I know that I'm still going a bit fast, which is really surprising when it comes to me, but the details between, the gaps that are still missing in my explanation, I want to cover them when we have the full picture. This is just to explain why we need the security groups. Just at least give some hints. Okay, so the firewall will filter the traffic, it will permit it, and the traffic will come back to the fabric, right? So we need to tell leaf 2 that this traffic that is coming back here is at a very different step than the traffic that was coming from host 1 to leaf 1. It's exactly the same traffic, right? It's the same source, the same destination, but actually this one and this one here are at two completely different steps, two completely different points in times. So we need to treat them completely differently. We need to be sure that here, leaf 2, it's not applying the same decision that leaf 1 was doing, because if it did, then what would be the ending? Leaf 2 would again redirect to the firewall, which would come back, redirect, etc. We would enter a loop, which is something we hate in networking, right? So we need to break it. Not break it, but not even allowing it to arrive. So we need to give leaf 2 the understanding that now this traffic here, even though it's exactly the same as the one here, we need to apply a different decision on it. The way we do this is by saying, okay, here, the source of the traffic, the ESG, is no longer 100. It is actually the ESG that we are matching here on this interface. So it is 1200. So now we are considering 1200 to 200 and no more 100 to 200. So this is the key of the solution. This is how it works in the backend. And actually, as you can guess it, when we are going to do some show commands to visualize all the contracts, our contract that we configured into the service policy, meaning this one, this one. So we will configure just one line actually, but in the back end, this line will be automatically split into different lines to insert in the middle the ESGs of the firewalls, of the service endpoints, for both the forward traffic, and the same thing will apply exactly for the reverse traffic. So exactly what we are being considering here for our example for the forward, it will apply for the reverse. It is the same thing because it's exactly the same logic. It's just that the ESG numbers will be different if we have two arms, okay? So in the backend here, we are considering 1200 to 200. And this will be a permit rule, since for our use case, for our example, we have just one sequence. If we had multiple sequences, it would still have another step here before being allowed, before being permitted by the last rule. So we have multiple redirects, and the last rule is a permit rule. The last thing that I want to mention on this slide is that, and sorry, I should have put my face up or remove it completely. The last thing that I want to mention is it might be strange to consider that the security group 1100, which corresponds to the endpoints IP addresses in the forward direction, is actually something we are being classified in for the return traffic. I know that now maybe it can be a little blurry, but just again have in mind the way that the traffic will flow across the fabric. Let me show you, but just before quickly, let me clean my screen. Okay, so let's again consider a forward traffic from host 1 to server 1. So it will first be redirected to the inside leg of firewall 1. Then it comes back. And here it is permitted towards server 1. When it comes back, through which leg is it coming back? The orange leg, right? So the firewall out leg. So in which group are we being classified? In the group of the firewall out leg, so the group 1200. So even though it's the one that we are mentioning here being reverse, it is still the one that we will be using for classification for the forward traffic. And exactly the same logic goes for the reverse traffic. So the reverse traffic, we would go from server 1 to firewall 1, and then come back from firewall 1 to be forwarded to host 1. When we come back from firewall 1, we are coming back using the purple leg. The purple leg, which is the firewall inside leg, and here we are being classified using the forward security group. So even though we have a forward and the reverse, it applies to the other way around when it comes to the traffic, but it really makes sense when you consider the traffic law inside the fabric. So long story short, what I want to say is that it can be, in the beginning, a bit surprising, but if you step back and you think, okay, how would I have done if I had needed to enable this inside the fabric? So now it starts making sense, because you need to tell the fabric how to consider the flow at different steps, how to understand in which step we are from the perspective of the traffic flow, which leg are we crossing for the forward, for the reverse, etc. And then all the pieces of the puzzle start to fit together. At least I hope so. Please tell me in the comments if it is starting to make sense. And the very last part of the configuration, okay, let me completely remove my face. It is defining the service chain. Now, this is very straightforward. I believe we have covered the most quote-unquote tricky part. So the service chaining, we are simply saying what is the load balancing method. So just to differentiate between the different traffics sent by the hosts to the servers, etc. So here we are using the most granular possibility, which is using the IP, a source and destination, as well as the source and destination protocol and the ports. So here it is TCP or UDP, the L4. Okay. And we are giving the set service firewalling. So we have, again, just one sequence number because we are having just one service inside our chain. Then we can go ahead to create our policy to redirect the SSH and permit the telnet and ICMP. So the configuration is quite intuitive. We say that we configure a policy map of type security. We give the name. And we say that for the class ICMP telnet, it is a permit. Actually, it's the default when we configure a policy map. And for the class SSH, we are redirecting to a service chain that is chaining, which was defined just above. And the very last step of configuration is come back to our VRF, blue VRF. And here we are saying that for the source 100 to the destination 200, we are enabling this client to server policy. And yes, quick remark again, as we mentioned it multiple times, here by default, the fail action is drop. If we want to drop the traffic in case of failure of a service, we do not need to mention it explicitly. It is the default action. If you want to do a bypass, we would need to mention it explicitly. And again, for a fail action to be detected and to kick in, we need to detect a failure to begin with. So we need to configure probing, etc. So this is just what we said multiple times. Now, if we take the configuration as a whole, this is what we have. So as you can see, it's actually quite straightforward configuration. I mean, it is still quite short if we consider all the steps, I mean, all the work that is done in the background by the Nexus 9 case. From a configuration perspective, it is still short, in my humble opinion. So we have the enabling of the feature, of the system routing template security group, the three features that we need, the security group, SLA sender, and ePBR. Our two classic ESGs, so clients and servers, the filtering for the traffic, the class SSH and the class ICMP telnet, then the policy map that is calling the two classes by giving the proper action on them. Then we have the security group the layer 4, layer 7 security groups for our firewall in leg and firewall out leg. The configuration for the service, so here it is ePBR service firewalling. We are in the VRF blue. We give the endpoints for the forward traffic and for the return traffic, and we give the appropriate L4, L7 security groups to which we need to map for our service. And we configure our chaining with the proper load balancing and what are the different sequence entries that we need to evaluate. We need to go through for our redirection of the traffic. So again, here we have just one sequence number, so we have just one service. And in the end, come back to our VRF and mention that we want to enforce a default deny. We give a default tag, so this is to be matched by the traffic that should not be matched in any contract. Actually, it's to cover the broadcast and the BUM actually. And the very last step is to give the contracts for our source and destination. So from 100 to 200, we want to enable this policy. So that is the whole configuration. And the last point that I want to do before we go to our lab is step back again a bit and see why we need all the pieces of the configuration and where does every piece fit inside the logic of the forwarding. It is going to be a bit challenging for me to illustrate this because I don't have a lot of space still available inside the slides, because I need still to put the configuration, the global drawing, and the drawing of the frame when we use the VXLAN encapsulation. So basically all the space that I have is this one. So as you can tell, it's not very, very wide. So yeah, it's not going to be easy, but still let's do our best, okay? And let's try to understand why do we need all the pieces of the configuration. Let's start by the easiest and the most straightforward. Okay, not to mention the features, because this is really the basics, okay? We need to enable the features so that we unlock all the capabilities that come after. So the security group 100 and the security group 200, these ones are the one to put the servers and the hosts inside the proper groups. So when host 1 starts to send ARP traffic, and the same for server 1, this ARP traffic is caught by the leaf 1 and by the leaf 4, which allows leaf 1 to put host 1 into the ESG client, and it allows leaf 4 to put server 1 into the ESG server. Then each of the leaves will start sending the mapping between the host and the proper tag through the route type 2 updates, which contains the MAC IP mapping. So all this is thanks to these configuration lines. Okay, now let's consider that host 1 sends traffic towards server 1. And let's imagine that this traffic is SSH. It means that here, for our original payload, the source IP of the inner header is 192.168.10.1. The destination IP of the inside header is 20.1, and the destination port, so D port, is TCP 22. Now, obviously, the original payload, when it comes to the source and destination MAC addresses, these ones are straightforward, right? It is the source MAC address of the host, and the destination MAC is the destination MAC of the Anycast gateway. It's just classic routing. So we will not cover this one. It will be received by the leaf 1 on the attached port. Let me again remove my face. Okay, so leaf 1 receives this traffic and needs to make a decision. What is the decision that leaf 1 will make? It will check the source, and it will see that the source actually belongs to the security group 100. It will check the destination, and it will see that the destination belongs to the security group 200. And it will check this TCP port, and it will see that, okay, we have a certain kind of traffic that corresponds to SSH. Okay, it will say, what do I need to do with this traffic? So let me check what do I have inside the configuration of the VRF in which I have received my traffic, which is the VRF blue VRF. So first it will say, okay, by default, I have a default deny. So it means that if I didn't have any kind of policy configured between 100 and 200, I would go ahead and drop the traffic. But it's not the case. I have actually a policy for the traffic from 100 to 200. So let me check what is actually this policy doing. So let me evaluate it. What is the content of this policy? It is this one. So it is saying, okay, if it is class ICMP telnet, meaning this block, I should simply permit it. Is it ICMP or telnet? No, it's not. It is SSH. So let me check if I have an entry for SSH, which I actually do. I have a class map that is matching on the port, destination port SSH, and I'm being told, okay, please go ahead and do a call to the service chain that is named chaining. Okay, so let's check what is behind this service chaining. So what's behind this service chaining is a specific kind of load balancing. So far, so good. And then I have a first entry in my sequence number, in my sequence list, which is set the service being firewalling. What is this firewalling? It is defined here, okay? And it is giving me the information of where should I send the traffic. Why is this important? It is very important because Leaf1 needs to build its VXLAN header. And there is a bunch of fields that it still needs to populate. So far, the only information that it knows is how to populate the information related to itself, meaning the information related to the source. When it comes to the destination, if it didn't have this block of set endpoints, it would not have a clue of how to build the outside header. Let's come back to the slide and let me clarify what I mean by this. So before the evaluation of this part, we are able to populate some fields of our frame. So here, sorry, I should have presented the frame, but you know, it's the classic one that we all know. We take our original payload. Then when it comes to the routing, we need to rewrite the inner source MAC of the inside, so the inner source MAC, the inner destination MAC. Then since it is VXLAN encapsulation, we have a VXLAN header, then a UDP header, then an external IP and Ethernet encapsulation with the source address, the outer IP source address, the outer IP destination address, and the least interesting fields, which are the outer source MAC and the outer destination MAC, which corresponds to the source and destination MAC addresses of the point-to-points that we are crossing across, across the fabric. So the interfaces between the leaves and the spines. So we really don't care about these two, okay? Let's come back to our traffic. I was saying that so far the leaf one only knows the information for itself. So it will allow it to populate the inner MAC source address, which is the router MAC of leaf one, and the outer source address, outer IP source address, which is the leaf one loopback one. Right? I mean, the loopback of the VTAP, which is usually loopback 1 for the Nexus 9K, and inside all the documentation referring to VXLAN. So it still needs to know how to populate the destination MAC. It still needs to know what to put inside the VXLAN header and what to put inside the destination IP address. But thanks to this block of configuration, it will deduce this information. It will see that, okay, the service to which we need to redirect is inside the VRF blue. So it will give it still one information here, because in the VXLAN header, we are encoding multiple informations. We are coding the VNI, the J bits, the A bits, and the source tag. And by the way, it already knows that the source tag equals 100. This information it knows. For the VNI, here it is the L3 VNI for the service VRF, which is, again, here we have just one VRF. So it is the L3 VNI of the blue VRF. And it's already being challenging to write. Okay. So in the VXLAN header, here we have the VNI, the L3 VNI of the header. Okay. Then we have two possibilities to send the traffic. So according to the load balancing, to the result of the hashing that we are using in the load balancing method, we will pick either the .1 or the .2. So let's say that we are picking the .2, just for the sake of demonstration. Okay, so we are picking 192.168.110.2. Leaf1 will do a lookup in its table to understand where 192.168.110.2 is actually connected. It will discover that it is behind leaf 3. Why? Well, simply because, again, when the 110.2 has started sending out traffic, it was caught by leaf 3, which updated its HMM table, and leaf 3 has sent a route type 2 update to the rest of the fabric to advertise the reachability of 110.2. So thanks to this, leaf 1 now knows that the destination of this frame should be leaf 3 IP address. So leaf 1 is now really happy because it knows how to populate the inner MAC destination now. Now it is the router MAC of leaf 3. And it also deduces that the outer IP destination is leaf 3 LO1. Okay. Now it still needs to populate the latest fields, which are the group and the G bit, not the group, the G bit and the A bit. So the G bit is equal to 1 automatically because we are doing GPO. If you remember, if we are in the context of classic VXLAN, the G equals 0, which is not our use case. We are doing GPO, so the G bit is necessarily 1. What about the A bit? If you remember from the theory part, we saw that when we have actually a policy saying from 100 to 200 do a redirection to the service chaining, we are actually breaking it inside multiple subcontracts. The first entry will say, okay, from 100 to 200 do a redirect. And if we are doing a redirect, then we should set the A bit to 0, which means that we are making the remote leaf think that we did not apply any policy, so that we force the remote leaf to reapply the policy. It will make sense when we arrive to leaf 3 and we study what leaf 3 does with the traffic that is receiving. And just to continue the split of this main contract into multiple subcontracts, the first line will be from 100 to 200 do a redirect. Then when we come back from the firewall, to 200, do a permit. So this is for the forward traffic. For the reverse traffic, it will be the exact same logic. It will say from 200 to 100, first do a redirect. Then when you come back from the firewall to 100, do a permit. And you might be thinking, what is this from firewall? But thanks to the discussion that we had when we were introducing the layer 4, layer 7 and their configuration and their importance inside the service redirection, we know the answer, right? The from firewall is being mapped to the proper layer 4, layer 7 that we have configured inside our configuration, actually. So it means that here for the forward traffic, the from firewall actually corresponds to the ESG of the orange leg. Again, because for the forward traffic, we are coming back from the outside leg. And so here, the from firewall is actually in the background, under the hood, corresponds actually to 1,200. And for the reverse traffic, the from firewall here corresponds to the purple leg, because for the reverse traffic, we are coming back from the purple leg, and here it corresponds to 1,100. And I apologize because we have taken it some steps further, because so far we are still on leaf 1, right? So we didn't come back to the fabric once we have crossed the firewall, etc. But just to give some perspective. Okay, so here, just to mention that in the very first step, the A bit will be set to 0, because when we are doing the the first, when we are treating the traffic that arrives, enters inside the fabric, and we are redirecting it, what corresponds to the redirection rule is the A bit being set to 0. So now leaf1 is really happy because it has populated absolutely all the entries that it needed. So it can simply go ahead and send the traffic to the spine, and the spine will route it towards leaf3. Okay, so now we are at the step of leaf3. Let me move to the next slide, which is exactly the same. It's just that it is clean. So we are now at leaf3. So leaf3 will go ahead and decapsulate. So it will remove everything because it sees that the traffic is for him, and it will read again the payload. Before doing the decapsulation, it has checked that the A bit was set to 0. Since the A bit was set to 0, it understands that it still needs to check its database of contracts. By the way, this database of contracts, we will be doing show commands on it when we go to the lab environment, so it will be clearer, and we will finally see what is behind the split of the main contracts into multiple subcontracts, etc. So coming back to the slide, leaf3 will say, okay, I have the A bit set to 0, so I need to reapply something inside the policy. It will it will do the exact same logic as leaf1. So it will retrieve the group of the source, which will be 100, the group of the destination, which is 200, and it will see that for 100 to 200, the rule is to redirect. So it will go ahead and redirect to the firewall 2 inside leg. Firewall 2 will eventually permit the traffic, and the traffic comes back through the outside leg. Now, once leaf3 receives this traffic, it will treat it differently than the traffic it received in the first place. Why? Because now it is receiving it from the orange leg, and the orange leg actually belongs to the security group 1100. So, in other terms, when leaf3 received the traffic here, the contract that it was considering was the contract from 100 to 200. Now, when it receives the traffic from the orange leg, it is no longer considering the contract from 100 to 200. It is considering the contract from 1200 to 200. And this line has actually an entry to say permit. So since it is a permit rule, it will simply do the classic forwarding. It will check where is the destination located and build accordingly the VXLAN encapsulation header. This time really nothing fancy. It will populate the outer IP destination header with the loopback 1 of leaf4, the inner destination MAC address with the leaf4 router MAC. And when it comes to the VXLAN header, let's see again how it will be populated. So the VNI is the one of the destination. So it is, in our case, still the L3 VNI of the blue VRF. The G bit will be 1. The A bit, since it is now a permit rule, the A bit will be also 1 to say, okay, now I have applied the policy. Please leaf4, when you receive the traffic, simply permit it. You do not need to apply anything anymore. And finally, the S tag, now, it is 1200. So the S tag on the first part of the forwarding was equal, it was equal to 100, and the S tag on the second part of the traffic, now it is equal to 1200. Then leaf4 will receive the traffic, it will decapsulate it, okay? It will check that the A bit is equal to 1, and it will simply allow the traffic towards the destination. So this is how the layer 4, layer 7 ESGs are being used. I know that, again, it's not straightforward. I hope that the explanations were still clear. And if there are still any doubts remaining, I hope that they will be cleared when we go to the lab and push everything inside the lab devices. So let's go ahead and push the configuration. So here we are back on the lab devices, and the way that I'm going to proceed is simply have the slides with the configuration on my other screen, and I will do some copy paste, because again, now we have covered absolutely every line of configuration. So it doesn't make sense to spend more time to explain it. Now my purpose and my goal is to push this configuration inside the lab environment and then do the proper show commands to visualize finally the contracts and see how the swapping of the source tag is being performed across the fabric. So what I'm going to do is send the commands to all the sessions. As you can see, this is what I have enabled here, so that we can simply go ahead and copy the commands. So first, let me do the application of the system routing templates, which by the way is already done. I have rebooted, but I have already rebooted the switches with this being enabled. So we can see that the commands were taken by all the leaves. Now, let me go ahead and put the commands for the security group clients and servers. Okay. And what I would like to do very quickly is just show you that if we configure just this line, which is the enforce deny, now obviously the result is what is not explicitly permitted is implicitly denied. So let's check that our hosts have been put inside the proper tagging. So show IP route 192.168, the client was 10.1. Sorry, 192.168. VRF, blue, VRF. Okay. That's very funny. So let me type it here with the auto completion. It will be easier. So show IP route 192.168.10.1 VRF detail, and then VRF, blue VRF. Okay, so here I see that the tag is 100. Now let me recall again this command with the 20.1. And we see now the tag is 200. Obviously, since I'm on leaf 1, the first one I learned it through HMM, and the second one I learned it through BGP. Nothing crazy, right? So now let me go to the host device, which is here, and let me do a ping. From the simulated host 1 to the simulated server 1. So the ping is broken, right? This is expected, nothing works because again, I did nothing in the VRF except doing a default deny, okay? So let's come back to our hosts and do the rest of the configuration. Sorry, to our leaves actually. So let's configure the class maps. Okay. The layer 4, layer 7 ESGs. And then the service and the service chain. And finally, the policy map and the application of the policy map inside the VRF. Okay. Then to visualize the result of the configuration, there are two commands that are very handy. It is show run security group, which will show all the parts related to the ESGs, and show run ePBR, which shows what is related to the enhanced PBR. I believe that there must be a command that shows all the configuration blocks in one output. I honestly didn't find it yet. So I'm using still the two commands and see it into two separate places, but still it's just two commands, right? So that's it for the configuration perspective. Now we are going to be able to go ahead and check what do we have from the perspective of the forwarding. So first, what we should see immediately is that the ping is restored. So the ping is restored because we are permitting the ping from the host 1 to the server 1. Now let's quickly see traffic that should be allowed and the traffic that should now be denied. If you remember in the beginning, and I believe we still have it here. Yes, we still have it. So we did an SSH to server 1 from host 1. And this should still be allowed now, redirected but allowed. So let's first check that it is allowed. And it is. And now let's check back something that should be denied now, which is the SSH from server 1 to host 1, which was previously still allowed. And we see that now it is being denied. So this is already a good point, right? What should be permitted is permitted, what should be denied is denied. But now let's check more outputs when it comes to the configuration of the contracts. And for this, I actually have some commands that I prepared inside my slides because some of the commands are not straightforward. Some of them are really intuitive and make sense, but other ones are more tricky to answer. It's because we need to check what is under the hood, right? And, you know, we are checking a level of detail that is very, very teeny. We are pushing the things very far. At the end of the day, when it comes to the redirection, we do not really need to know all those details, right? This is being carried, this is being taken care of by the switches themselves directly for you by the NXOS code. So, and this is also why the commands are pretty tricky. It's because we are trying to verify something that is really advanced and what is under the hood. So coming back to the lab environments, let's first do some straightforward commands like show ePBR service chaining. Service chain, and I give the name of my chain. So here we see that we have just one sequence in our chaining, and we are doing load balancing between the 110.1 and the 110.2. Hello back. Apologies, I have been interrupted into my recording, and in the meantime, I got disconnected from my leaves and hosts, etc. So I just reconnected, and we were going to check the state of the services. In our use case, again, we have just one service, but the command is pretty straightforward. It is simply show ePBR service and then the name of the service. So here we can see being displayed the 2 firewalls that we have configured. And for each firewall, we have the quote-unquote forward IP address and the reverse. So 110.1, 121 for the firewall 1, 110.2 and 122 for the firewall 2. If we had configured some probing, tracking, etc. for our hosts, for our firewalls, our service endpoints, we would have seen it here. Now let's move to the less intuitive commands. And by the way, maybe I will just copy paste it. It is actually the main one, the central one. It's really this one. Show system internal policy manager DME zoning rule. Because actually what it shows is what the NXOS firmware does in the background when we have configured our policy. Again, we have checked multiple times what is the configuration for our VRF, but let's, for the sake of clarity, let's remind it. So our blue VRF, what do we have inside of it? We have the enforce tag with the default tag for the BUM matching, we are enforcing a default deny. And then we have a contract between our source 100 and our destination, which is 200, which is calling this policy. And just with these 2 lines of configuration, the device is deducing in the background multiple lines, okay? So as you can see, we have some lines that are mentioning our security groups that we defined explicitly, the 100 and the 200, but in the between, we also have some contracts between 1100 and 100, on the opposite 1200 and 200, etc., These contracts is what has been added in the middle by the configuration of the service chaining that we did and the ePBR service that we are calling. So it is thanks actually to, by the way, it's not to this command, it is with the Shoren ePBR. It's thanks to this security group that we are inserting in the middle that the NXOS is deducing what to put inside the contracts. So actually, again, it's multiple places of configuration that are computed internally to finally being able to deduce these rules. So let's quickly go over the main columns of this output. Then I will go back to the slides where I took a copy paste of the lab environment, actually of the outputs, and we are going to go through the lines on the PowerPoint. Why will I move on the PowerPoint? Is because on the PowerPoint I can easily use my pen to, how do we say, to highlight each lines once we have done it, once we have gone through it, okay? That's the only reason. Okay, so coming back to our output. First, we have a column that is rule ID. Really, this column, it's, as the name states, it's just an ID for the rule. We do not care about what ID has been given at any point in time. It's just a way to give a specific numbering for a specific rule. It's not taken into account at all when it comes to assessing what is the rule that we need to apply. What matters when it comes to the assessment is actually the priority of the contract and also obviously reading the ESG, the source tag, as we have mentioned multiple times inside all the theory that we have checked together. So this is just an ID. Then we have the column for source ESG and the dest ESG. So this is self-explanatory. What it's telling us is when we have this source and we have this destination with some specific additional things, what action shall we take? So let's continue. Then we have a column that is filter ID. Here we see some entries that are named implicit, and we see some ID, right? Some IDs that we didn't explicitly configure. So what can be those IDs? And I'm sure that you have guessed it by now. What we did configure actually manually was the class maps to filter to match on the proper traffic. So to using the proper filter selectors to match on SSH, ICMP, Telnet, etc. So our guess is that behind these numbers that we are seeing on the screen, we are referring actually to those class maps that we have configured. And it's exactly the case. It's just that we do not see it here, but there are some commands that we can use to display what's behind the filter IDs. We will display it right after. Let's continue our journey in the columns. Then we see a column that is named dir for direction. So as you can see, we have some things that are by dir and unidir and also unidir ignore. For the moment, let's leave this column aside. We will come back to it a bit later. The operational status is the most straightforward column in the world, right? It's just saying that, okay, these filters are enabled. Then we have a scope. So the scope is basically just to refer to a VRF. So for example, you see that everything that is related to our blue VRF has actually a scope of 4. Everything that's related to the default VRF has a scope of 2. Management is 1, and egress load balancer resolution, which is also one of the default VRFs that come with the train 10, it has a scope of 3. So what matters for us and what we will be exploring is everything that has a scope of 4. Then we have a name for the policy that we are referring to. So the policy that allowed us to install that specific line inside our zoning rules. So we can see that most of them come actually from the policy that we have configured together in the previous steps, right? Then we have 2 lines that are actually installed. Sorry, I did the wrong path. That are actually installed implicitly. So you can see these 2 lines that have an implicit, have a name of blue VRF. So these are the 2 default rules that come when we do an enforce deny. So we have a line that says, okay, whatever to whatever by default it is denied. And we have this line with the default tag that we are configuring to allow the traffic that is related to BOM. Apart from this, again, what matters for us and what we have explored and we continue to break down is what is related to our policy that we entered manually. Then we have the action. The action, it is very important because it is here that we are saying, are we simply permitting or are we redirecting? So this is what will be translated inside the header by saying, are we setting also the A bit to 0 or to 1? When we do a redirection, we set the A bit to 0. So we force the remote leaf to reapply a policy. When it is a permit, we set it to 1 so that the remote leaf, when it receives the traffic, it simply forwards it to the destination. And additional thing, you see that when we have a redir action, we are referring to a desk group. Again, what is this desk group? It's not explicited into this command. So it's exactly the same logic as what we were mentioning for the filter ID. There are some commands that we can use to see what is actually behind this desk group 1 and desk group 2. And as you have already probably guessed it, what we have between one of them is the 2 IP addresses of the purple legs, so the inside legs, and behind the other one, we have the 2 IP addresses of the outside legs of our service, which I hope now everything makes sense and everything fits together good. Sorry, I'm getting lost between all the buttons. And the priority. So the priority, the lower the number, the better it is. So when we have an explicit rule between 2 ESGs, it is the one that is evaluated first. So actually, if we have nothing that matches a priority of here 7, we will go down to be defaulted by the other ones. I'm not sure that to be defaulted is an appropriate English terminology, but you understood it, right? So the lower the priority, the better it is to being evaluated. So this is what is important actually when it comes to which line should we evaluate. It's not the role ID at all. So now that we have covered the details of this table, I would like to show you the commands that allow us to understand what is behind the filter ID and understand what is behind the desk group. I mean, not understand because the understanding, I believe now we are really clear, but how to visualize it. So to visualize the filters, the command is this one. Show system internal policy manager DME zoning filter. By the way, let me just zoom out a bit and recall the line. Okay. Let me zoom again. I hope it is still readable, but since the lines have plenty of outputs and I would like to really display the output on a single line, it's a bit tricky. So let's see just one of them and then we will going to see the details for right after in the slides. Sorry. So let's take the very first step in our forwarding. It is from 100 to 200. And I would like to take the simpler one, which is the permit. So if you remember from our configuration, what did we choose to permit explicitly? I mean, sorry, what did we choose to permit without a redirection? It was the ICMP and the telnet, right? So the ICMP and the destination port TCP23. So we can imagine that behind the filter ID 3, we should see ICMP and destination TCP23. So let's check this. So this is the filter 3, and as we can see, it's exactly that. So we have an ICMP here. Sorry, the filter is mentioned there. And we have also a destination port of TCP. And as you can see, source from, so it is a range. So whatever source port between this port and this port is included here, but we didn't specify anything for the source port, right? So we have just unspecified. To the destination from ports to ports. So again, it is a range of destination ports, but again, for the range, it was from 23 to 23. So it was just one port. So we are just matching on TCP23. Now, if you remember also multiple times, I said, okay, for our class map, for the ICMP-telnet, we could have subdivided it into, not subdivided it, sorry. Instead of creating just one class map, we could have created two. One class map for ICMP, one class map for telnet. In that case, it would have been translated into 2 filter IDs, right? But this doesn't matter. You know, it's just again how you want to handle your filters, how you want to group them, etc. Most probably in a production environment, we would not put ICMP with telnet. We would not have telnet anyway, so it is the problem, right? But that's the generic ID. So coming back to the slides, now we have understood what is behind the filter ID. Now the latest things, it is to understand what's behind the destination groups when we are doing actually redirection. And the command, it is this one, show system internal ePBR, info service chaining, and then our chaining. Here we see what are all the groups that matters, that we are invoking for our chaining. And in our use case, again, we have just one service. So we still need it for the forward and the reverse. So we have two groups, group ID 1 and the group ID 2. So you can see indeed it is those groups that we are calling through our service chaining. And the additional command to explicitly display the IP addresses would be this one, show system internal service manager group 1 detail. So we see that behind the group 1, we have basically the IP addresses of the purple legs, meaning the inside legs of firewall 1 and firewall 2, meaning 192.168.1.1 and 192.168.1.10.2. And you have guessed it, if I recall the exact same command this time by filtering on the group 2, I have the 121 and the 122. The other line destination name, it is still 110, it's still 110.1 and 110.2. This is just a name. What matters for us inside this output is actually really the destination address. So we see that for group 1, it is the IP addresses in 110, and for the group 2, it is the IP addresses of 120. So that's it for the breakdown of the contracts. Now let's come back to our slides. Okay, so here we are back again to the slides. As you can see, I simply did some screenshots of the outputs. Actually, the rule IDs are probably not the one that we have seen together previously, because these screenshots are from my lab reproductions when I was preparing the video. So the rules IDs are probably not the one that we are seeing now live again, but it really doesn't matter, because as mentioned previously, what matters is all the rest of the entries. But still, even though the rule IDs are not the same, the rest is exactly what we have checked together in the live output of our lab environment, because the configuration is the same, right? The configuration that I prepared in the slides is the one that we pushed together. So hopefully the output is the same. So now it's going to be very funny to go through the lines and not mess up between the lines. So please bear with me. First, we are going to check the lines that come from the forwards traffic. So from 100 to 200. Knowing that between 100 and 200, what we will be inserting is 1200. I will not explain again why it is 1200 specifically. It was mentioned in the minutes before in the videos. So we will have one line for 100 to 200, then one line from 1200 to 200. And actually we will have multiple lines, because some will refer to the SSH and some will refer to the ICMP antenna. So let's check this together. What is the first line that we have from 100 to 200? It is the 4105, right? So let's check it. What does it say? So 100 to 200 with the filter ID 3, we have a BID rule. It is enabled. It is in the scope 4, which corresponds to our VRF, blue VRF. And this line comes from the policy clients to server policy. And here the action is simply permit, and we have a priority of 7. So here we are permitting what's behind the filter ID 3. So let's check the filter ID 3. The filter ID 3, it covers ICMP. Okay, back and forth. ICMP. So this is the ICMP. It's not easy. You should try it. And then we have the second line for 3, which is the destination TCP. Okay, destination TCP of 23. Okay, and while I'm doing this very funny exercise, Actually, I decided to change my mind. We will not check the forward, first the forward, then the reverse. We are going to do the forward for this one and check immediately the reverse so that it makes sense and we have completed at least one flow end to end. Then we will go to the next one. I believe it will be better because it will allow us to understand what is behind this BIDIR, which is very fundamental and we didn't touch it yet, even though we said multiple times that we are considering the return flow, right? So how is the return flow permitted, by the way? So the return flow is permitted automatically by the configuration. So the configuration will take care for us to ensure that when we are permitting the traffic from A to B on a specific port, then the return traffic from B from that specific port to A is also permitted. How does it translate into our outputs? Well, first, for the forward traffic, it will be coded with an entry that is BIDIR. And for each BIDIR, we will have automatically populated for us a rule with a direction that is unidir ignore. So let's check what is the return flow that corresponds to the 3 BIDIR, which should be from 200 to 100 for ICMP and from Telnet. So it is actually this one, the rule 4106. It says, okay, from 200 to 100, for the filter that is 32771, we have a rule that is unidir ignore. It is enabled. It is for our VRF blue VRF. It comes from our same policy. It's a permit, and it has a priority of 7. So let's check what is behind 32771. It has 2 lines. So one is in the very bottom. What does this line say? It says that it's for the source port 23. It's no longer the desk port. It is the source port 23. Okay. And the other line, it is to match ICMP. As you can see here, we have the ICMP. So the filter ID 32771 is the mirroring of the filter ID 3. And again, it has been populated for us automatically with the configuration. And this is also why I was saying previously that plenty of stuff that are done in the background with the configuration that we have pushed. And we do not need to care about plenty of stuff. Like we do not need to care about the configuration required to allow the return traffic. It is automatically populated. If we didn't want to, we could enforce it. But if we want to, which is normally the majority of the use cases, we can simply just let the configuration as we did. So this was for the permit. Now let's check out what is supposed to be redirected. So coming back to the forward flow from 100 to 200, so the line 4101, okay, from 100 to 200, with the filter ID 1, we have again a rule with BIDIR, okay. So the scope is 4 from our VRF, and it comes from the policy that we configured together. Here we have a rule of redirect, and we are redirecting to the destination group 1. Now again, the destination group 1, we have checked what it means, so we can see it with this command, and then the additional command that gives us explicitly what are the IP addresses behind these group IDs. I believe this is really clear. Let's not speak again about it. Let's rather check what is behind this filter. So the filter ID 1, it is here in the table of the filters, and as we can see, it is for destination TCP ports from any port, because the source is unspecified, to the range that comes from 22 till 22, so it means exactly the 22. So this one is a redirect to the destination group 1. So again, if you remember our drawing, and this time I will ensure that my face is not covering what I am drawing, we saw that we had the leaf 1 here, leaf 3 here, with the source here, the firewall there, and the destination was here. Sorry, leaf 4 with the server. Okay, so this rule that we just considered from 100 to 200 with the redirect, it will be evaluated here, and it will be evaluated here. So on the front panel port of leaf 1, the one that is connected to the end host, sorry, to the host 1, the source which is host 1, And it's also evaluated by leaf3 for the traffic when it receives it from the fabric. So this is what is evaluated, and it has a rule of redirect. Then the next thing that we need now is how to treat the traffic that comes back from the firewall to hit leaf3. So in that case, it will be the rule 4102 from 1200 to 200. This one is with a unidir, it's unidirectional. And it comes also from the policy that we configured. And this one is just a permit, as you can see. So it means that here we are just permitting the traffic to the destination. And these rules will be, so the 4102 is what will be evaluated by leaf3 for the traffic that comes back from the orange leg, and also for the traffic on leaf4 that comes from the fabric. I will not touch again the return traffic because you guessed it, and it's exactly the same logic. Just have in mind that we have broken, I believe, all the major steps and the key pillars to understand what does everything, where does everything fits. Sorry. So what can I say? I'm thinking out loud now, checking again what can be missing. Yeah. So the return traffic, actually, it comes from the 200 to 100 with the unidir ignore, thanks to the bydir that we encoded in the first place. And the 32769 is the mirror of the other filter. That was filter 1, if I recall correctly. Yes, 1 was to destination port 22, and the 32769, it is for the source port 22. And again, we will have the swapping of the tags, not of the labels. Right. Now, the latest thing that I would like to show is maybe a capture on leaf4, because it is actually on leaf4 that we are receiving. So it's on leaf4 that we are receiving the traffic that is destined towards server 1. It's easier to do the capture on leaf4 because we are anyway we are crossing this interface, right? I'm not sure of which leaf we will be crossing for the specific traffic, if it is leaf2 or leaf3, and I want to capture the traffic with the final label on the path. So I would like to do a quick eth analyzer with the span to CPU to show what would be the tag on the VXLAN header for the traffic that is received by leaf4 in the use case of ICMP and in the use case of SSH. So let's do it together. So we are back on the lab. Let's quickly check what is the interface that is connected leaf4 to the fabric. So to spine 1, it is actually the interface 153. So let's configure a monitor session on this interface. So monitor session 1, the source interface will be our 53, and we are redirecting to the CPU. Okay. Then let's do an eth analyzer. What was it? Local interface inbound, and we are doing mirror to CPU. Okay, let's use a display filter to capture only on the destination IP address, being the server 1. 192.168.20.1. And yes, let's display the details. Okay. So now we are going to go to the hosts and send a ping. Sorry, to the host device, so the Nexus 9K that is allowing me to simulate everything, and send a ping from the host 1 to server 1. So I'm back on the device hosts. Let me again display the interfaces, and we are doing a ping. So we said to the server 1 from the simulated host 1. Now let's come back to Okay. I'm not sure why it stopped, but let me do limit capture frame being 0. So here I'm sure that it will not stop. And go back to the host. Okay. So here we captured some packets, and let's see the VXLAN header. Actually, let's double check that it is exactly the one that we need. So we can see that the inner header is from 10.1 to 21, right? And if we check the VXLAN header, we see that the group policy ID, it's 100. So it typically shows that this packet didn't have any swapping of tags in the process of being forwarded across the fabric. Why? Well, because it was simply permitted, right? ICMP is simply permitted from ESG 100 to 200. So this ESG, the source tag, will be simply maintained across all the fabric. Now let's stop this capture. I will call it again. Now let's go to the host device. And instead of a ping, let's do the SSH to our server 1 from our host 1. So the SSH went through. Now let's go to our capture and see what we have. So here we are seeing that we have a destination port of 22. So far, so good. From the 10.1 to 21. And if we check the group policy ID, it is 1200, right? So here we see that it has been swapped in the middle. So it went through the firewall before being redirected to the destination. So again, if we put them side by side, when we had the ICMP, which was simply permitted, so the group was the original one. And now that we are doing the swapping, because it is SSH and SSH, we have redirected it, we have a source tag of 1200. So that's it. Well, this brings us to the end of the video. I hope it has been useful. Please let me know in the comments what you thought of it and even what you would like to cover when it comes to service redirection. With that said, thanks a lot for watching, and I will see you in the next video. Please take care.